JUICE is coming back to Earth, but not for long. The spacecraft is doing a double world first, the first ever Lunar-Earth flyby and the first ever double gravity assist manoeuvre. Let's learn more about these flybys, why they're important and why it's taking us so long to get to Jupiter. Last year, our Jupiter Icy Moons Explorer, also known as JUICE, set off on its 8-year journey to Jupiter. JUICE is on its way to study Jupiter and its 3 largest moons, Callisto, Europa and Ganymede. The mission will investigate these moons' potential to support life by examining their subsurface oceans. JUICE is expected to arrive at Jupiter in July 2031, 8 years after launch, after a series of flybys of Earth, Venus and the Earth-Moon system, the first manoeuvre of its kind. But why is the journey so long? At their closest point, Earth and Jupiter are separated by almost 600 million kilometres. At the time of this video, JUICE has already travelled over 1,000 million kilometres, yet it's only 15% of the way there. The answer depends on a variety of factors that our flight dynamic experts know well, from the amount of fuel used to the power of the rocket, mass of a spacecraft and geometry of the planets. What are the challenges to get to Jupiter? 1. The Earth is moving. On the surface of Earth, typically the fastest way to travel somewhere is the straightest possible line. However, in space, straight lines are a massive waste of energy. When we look up at the night sky and track the motions of planets, moons, stars and galaxies, you'll see they're always in motion around another object. When we launch a rocket, it doesn't leap from a still Earth, but from a planet zooming at about 30 kilometers per second around the Sun. As such, a spacecraft launched from Earth already has a great deal of orbital energy, the only unit that matters when determining the size of an orbit around a central body. Just after launch, a spacecraft is in more or less the same orbit as our planet is around the Sun. To break free from this orbit and fly in the shortest possible straight line from Earth to Jupiter would need a big rocket and a lot of fuel. It can be done, but the problem is you'd then need even more fuel to break and go into orbit around Jupiter and not be flung past it. 2. Jupiter and Earth are both moving and not on the same route. Jupiter and Earth are always moving with respect to each other. This means at their furthest distance, when they are on opposite sides of the Sun, they are separated by a whopping 968 million kilometres. The shortest distance between them is just under 600 million kilometres, when they are both on the same side of the Sun. But they're only in this position for a moment before the distance grows again, and the distance never remains constant. All the solar system planets are moving at different rates in their orbits around the Sun. Launching a spacecraft is like throwing a ball at a moving target from a moving vehicle, not an easy feat. Engineers must calculate the ideal time to make the jump on a circular path from Earth's orbit to where Jupiter will be when the spacecraft arrives, not where it is when the spacecraft leaves Earth. So assuming we have the most powerful launcher available and we launch on the shortest trajectory at the right time when the planets are aligned correctly, how long would it take? Early space missions such as the Voyager and Pioneer probes made the journey in less than 2 years, and the fastest any object has travelled to Jupiter was the New Horizons mission. Launched on 19th January 2006, New Horizons made its closest approach to Jupiter on 28 February 2007, taking a little over a year to reach the planet. However, all these missions continued onwards, receiving a boost from Jupiter, but none were captured by the orbit like JUICE will be. 3. We want to be captured by Jupiter's gravity, not boosted by it. To get into orbit around the huge planet, we need to lose some energy, but slamming on JUICE's brakes at Jupiter would require an enormous amount of fuel. Engineers need to control the spacecraft's mass, balancing the amount of fuel with the instruments it needs to carry to complete its mission. The more mass the spacecraft has, the more fuel it needs to carry, which increases its weight and makes it more difficult to launch from Earth. JUICE is one of the heaviest interplanetary probes ever launched, at just over 6,000 kilos, with the largest suite of scientific instruments ever flown to Jupiter. To get a spacecraft into orbit around another planet, we must match its orbital energy. When JUICE was launched, its orbital energy was the same as Earth's. It must gain energy to overcome the pull of the Sun's gravity, and will do so by stealing some orbital energy from Earth and Venus. Depending on the relative direction of motion of the planet and the spacecraft, a gravity assist can either speed up, slow down, or change the direction of the mission. The spacecraft also deflects the planet, but by such a minuscule amount as to be insignificant. Nonetheless, Newton's third law of motion has been preserved. To every action, there is an equal and opposite reaction. The world of orbital mechanics can be a counterintuitive place, but with a bit of patience and a lot of planning, it allows us to do a great deal of science with just a little fuel. So, JUICE is taking the scenic route, using the gravity of other planets to carefully adjust its trajectory through space and ensure it arrives at Jupiter with precisely the right speed and direction. This incredibly complex, constantly evolving route has been carefully planned out by JUICE's dedicated mission analysis team over the last 20 years. Somewhat counterintuitively, using the Lunar-Earth flyby to slow JUICE down at this point in its journey is actually more efficient than using the flyby to speed it up. If we had instead used this flyby to give JUICE a boost towards Mars, we would have had to wait a long time for the next planetary flyby. This first braking manoeuvre is a way of taking a shortcut through the inner solar system. JUICE will come extremely close to both the Moon and Earth, meaning that real-time pinpoint accuracy is required in all navigation manoeuvres. During the flyby, operators will keep a careful watch on the data coming down from JUICE, making any tiny adjustments needed to keep the spacecraft on the right course. Lunar-Earth flyby provides a prime test environment for instrument teams to collect and analyse data from a natural surface in space for the first time. For some instruments, this is the only opportunity to make certain measurements during JUICE's entire 8-year journey to Jupiter. It will give scientists and engineers the chance to calibrate their instruments, smooth out any remaining issues, and who knows, they may even make some surprising scientific discoveries. This event will be a world first. It will change JUICE's speed and direction to alter its course through space, but it's a daring feat. The slightest mistake could take JUICE off course. Thanks to this flyby, Earth will bend JUICE's trajectory through space, braking it and redirecting it on course for a flyby of Venus in August 2025. From that moment on, the energy boost will begin, with JUICE being whizzed up by Venus and then twice by Earth. The space exploration equivalent of drinking 3 back-to-back espressos. Once JUICE arrives at Jupiter, it will get close to Jupiter's moons, trading energy with them that they've held onto for billions of years, to get a view of these environments like never before, helping us answer some questions such as, could there be life under the frozen oceans of Ganymede, Callisto or Europa? What can we learn about the formation of planets and moons throughout the universe? Through the wonder of flight dynamics, by trading energy with the universe, we will soonish find out.